So now we're going to work on another finite state machine problem, this time going from a design, description, and state machine to a FSM circuit. We had just completed going from an FSM circuit to a state machine. So now we're going to go in the reverse. So here's our problem description. From the following output sequence, design a synchronous counter that repeats the given sequence indefinitely. You should only provide illegal state recovery from states 3 and 4 and direct these states to state 6. Use a D flip-flop for the most significant bit, a T flip-flop for the middle bit, and a JK flip-flop for the least significant bit. A more output Z is high only when the count is less than 3 in the intended counting sequence. Show a present state next state table and state diagram that accounts for used states. The output sequence should be 26150. Make sure all excitation equations are in reduced form. And it says don't draw the circuit, but we will go ahead and draw it so you can just see the completeness of everything. Alright, so we are starting with knowing our output sequence needs to be 26150. So this is the sequence we need to create, and we're going to do that by creating states to represent 26150. Now notice our largest number is 6, which in binary is 110, and we need 3 bits to represent that. So we're going to need 3 bits to represent our states, and if we have 3 bits, that means we have a total possible number of states of 8, or 2 to the 3. So that's what it means by having unused states, which you'll see in a moment. Okay, so let's go ahead and see how this is going to look in a state diagram. So we have state 2. I'm going to go ahead and make a legend first. We're going to have 3 state variables. I'll call them y1, y2, y3. y2, y3. And we're going to have one more output Z, and I mentioned that the more outputs get put in the state bubble. The reason they get put inside the bubble is because they're only dependent on the state and not on the inputs. Alright, so there's our legend. And let's go ahead and draw the state diagram. So the first state we're going to be in is the 2 state, the 0, 1, 0, representing the number 2. And if you recall, a more output Z is high only when the count is less than 3. So 2 is less than 3, so our more output Z is going to be a 1. Alright, so from 2, we want to transition into state 6. So we're going to have a 1, 1, 0, and a more output of 0 because that's not less than 3. Then that's going to go to state 1, 0, 0, 1. And it's going to have a more output of 1 because that's less than 3. Then it goes to 5. So 1, 0, 1 for 5. That's not less than 3. And then back to 0. Oh, not back to 0, to 0. 0 is state 0, 0, 0. That is less than 3. And we want this to repeat indefinitely, so then we want to go back to state 2. So notice there's no inputs that need us to transition. We just automatically go in this order over and over again. We don't need a special input to tell us to go there. We're just going to go there at the next clock cycle. And we're going to repeat this sequence over and over again. Now, we used 5 out of 8 possible states. So what are the remaining states? We have state 3. We didn't use state 3 in our sequence. We have state 4 and state 7. So these are the unused states. And it says up here we need to provide illegal state recovery from states 3 and 4 to state 6. So what it's saying is if we, for some reason, end up in these illegal states, states that we weren't supposed to end up in, we should recover, meaning go back to some known state. And in this case it says recover to state 6. So 3, if we end up in state 3, it says recover to state 6, or if we end up in state 4, recover to state 6. And it didn't say what to do if we end up in state 7, so it's just gonna hang out over here. Now, since these states are now used because we've provided recovery for them, we have here again that output Z is high only when the count is less than 3. So 3 is not less than 3, so its output here is going to be 0. 4 is not less than 3, so the output is 0. And because if we end up here, we're just going to stay here forever because we don't have any illegal state recovery, we don't care about the output in this case. So it's a don't care or a dash. Okay, so now we've drawn a state diagram, and we can now use the state diagram to create our PSNS table. And we're going to start with writing our present state on the left-hand side of the table. And we don't have any external inputs, so all we're going to have is the present state variables, y1, y2, and y3. And then we're going to go ahead and write the next state variables, y1 plus, y2 plus, and y3 plus. So I'm doing this because we already have this information in the state diagram. We're then going to come up with the excitation variables. And the excitation variables, it said in the description that a D flip-flop is used for the most significant bit, so that is y1. So we're going to have a D excitation variable for the y1. It says a T flip-flop is for the middle bit, which is y2, so we're going to have a T. And then we're going to have a JK for the least significant bit, so we're going to have a J and a K. And then we have our output Z. Okay, so how are we going to fill out this table? Well, we've got 3 inputs here, 3 present state variables. So we're going to have 8 possible combinations. I'm just going to go ahead and write those out. I hope I don't run out of room. All right. Now, if we are in state 0, what is the next state we go to? We go to state 2 next. If you look back at your diagram, when you're in state 0, you're going to go back to state 2. So we're going to have our next state as state 2. If we're in state 1, that's this state, we're going to go to state 5. If we're in state 2, we're going to go to state 6. If we're in state 3, that's one of our illegal states. We've provided illegal state recovery to state 6. If we're in state 4, again, we've provided illegal state recovery to state 6. If we're in state 5, we go to state 0. If we're in state 6, where's 6? There it is. We go to state 1. And then if we're in state 7, we just don't care because we haven't decided to deal with that state. Okay, so now that we have described our present state, next state based on the state diagram, we're now going to figure out what excitation variables we needed in order to make that transition. So remember, y1 is our most significant bit of the state variables. That's going to be governed by a D flip-flop. And I've gone ahead and put the excitation equations, or rather tables, for the D, T, and JK up here so you can remember that. So with a D flip-flop, in order to transition from 0 to 0, what does D have to be? So you look at your table, you see to transition from 0 to 0, D needed to be a 0, so you get a D of a 0. For y2, to transition from a 0 to a 1, what does T have to be? T has to be a 1. Again, you could look at the table. Transition from 0 to a 1, T needs to be a 1, or you can remember that T means to toggle, so you needed to toggle the 0 to get to a 1. And JK for y3, we go from 0 to 0. If you look at your JK excitation table, to go from 0 to 0, J needs to be 0 and K is a don't care. Alright, let's do another one of these. Here we're going to transition for Y1 from 0 to 1. Remember, it's using a D flip-flop. So in a D flip-flop, the next state gets whatever D is. Because we want our next state to be 1, D needs to be a 1. You could also look at your table to go from 0 to 1, D needs to be a 1. Now we look at Y2. We go from 0 to 0, so that means we don't toggle, so T is a 0. A Y3, we go from 1 to 1. Look at our table. 1 to 1 means a J is a don't care and K is a 0. Okay, so this is how you go about it. You just go row by row. I'll go ahead and just do one more row and then fill it in. So Y1 going from 0 to 1 with the D flip-flop. D flip-flop. It's actually very easy to fill in this whole column of D because whatever Y1 next state is what D needs to be. So I'll just go ahead and do that. So we got a 1, 1, 1, 0, 0. Don't care. And the toggle, you're only toggling if Y2 next state is different than Y2. So I'll just go ahead and fill that in. 0, 0, 1, 0, 1, don't care. And the JK, I often look at the excitation table for the JK. I'm just going to go ahead and fill that in. 0, don't care 1, 0, don't care 1, 1, don't care, and don't care. Okay, so really what you have to do with these is just go row by row. Now the output Z is dependent on the present state. So Z being a more output only depends on the present state. When I'm in state 0 is over here, my output is a 1. When I'm in when I'm in state 1, my output is a 1. State 2, my output is a 1. Remember, anything less than 3. And so I'm just going to have zeros for the rest of these because they're all greater than or equal to 3. I'm losing my rows. Sorry. Whew. Alright, so now we have created the present state, next state table with all of our excitation variables and outputs combined, and now we need to use this to create our next state logic, which will make use of the excitation variables, and our output decoder, which will make use of the output variables. And I will do that in the next video.